Uh, Hello, everyone. I'm Chang. I, uh, I come from Zhengzhou University, and I'm a PhD student of Michael Fuchs. And this paper is joint work with Professor Fuchs and Professor Yu over there. And the story starts from phylogenetic networks. Given X finite set it collects several species. And a short story here is biolog uh, biologists want a giant live tree that can store every species on their leaves. But the reality is not, because we have some reticulation events. So I need to extend tree into a phylogenetic network. And phylogenetic network is a rooted simple deck. We have four types of nodes. We have one root and several leaves, which are bijectively by X. And we have two kinds of 3-degree nodes. One is tree node and reticulation node. In recent decades, there are several kinds of classes of networks are suggested. And in mathematical sense, that we put some restriction on the reticulation nodes. Here, I suggest few classes of networks. In this pole set, the up-down order is roughly like how harsh condition you put on reticulation. If you have no any restriction, then you will be the top one. You are universal networks, you are phylogenetic networks. But what if you put a very harsh condition so that no reticulation satisfies this condition, that it will downgrade to a phylogenetic tree? I will introduce as my topic, I will introduce the tree trial network here and Go network. The first tree trial network is that every non-leaf node has at least one non-reticulation child. The sentence contains two negative statements, so you may be confused. So let's see the example here. On the left-hand side is a tree trial network. On the right-hand side, this node, if you can see that, both of these trials are reticulation nodes, so against the rule, so it's not a tree trial network. And next, a Go network that is every reticulation node is in a tree cycle. A tree cycle is mean, for example, this is a reticulation node. We find a tree cycle that is a two path. The first one, and the second one is just go straight forward. And you will find that a tree cycle is composed of two disjoint paths, and they are composed of tree nodes except the bottom one. But the left-hand side, the example is not a Go network because the bottom reticulation, you won't find another path that will form a tree cycle because you will essentially touch another reticulation. Here. And on the right-hand side is a Go networks. These two examples is told us that the differences between tree trial and Go networks are not empty, respectively. Okay. And there are some several results for TCN, which is the number of the tree trial network with N leaves, and the GNN. The first one is given in 2021. The interesting part is that there is a stretch exponential term in the middle, but we don't have the multiplicative constant. Another result for GNN here is opposite. We have the multiplicative constant, but we don't have stretch exponential term here. I want to talk about it further about how we get these two results because they have totally different method. The first one, TC networks, we find that TCN is actually asymptotic to TCNN minus one with a multiplicative constant. You also say that the maximum reticulated TC networks is TCNN minus one. And we move forward and we look further in TCNN minus one and we get the results from the following steps. But I want to talk about Go network. The Go network is use a totally different method. The first we use the so-called component graph method. I will talk about later. And then we use Laplace method and the result from band enrichment in 1984. Okay. So let me introduce the component graph methods. For example, on Go network, on the left-hand side is a Go network. And first step, we cut each in degree of every reticulation. And the network will split into several parts and we call them components. And second, we replace each component by a node, just like a pinned component will become a node on the right-hand side. And then we have three dots here, three nodes here. And we connect each node if they are connected on the original graph. And we replace the double edges by one edge with an arrow on it. The arrow is not talk about the direction, it's just a mark. It's just mark on the edge. But if you see on the right-hand side, actually it looks like a tree, but it's not a tree because there's a degree of two node. So we also compress the node into this part, into this shape. We compress it. So actually there's a lemma says that the component graph of a Go network without errors is a phylogenetic tree. In this case, you will see that without errors, but actually we have an error in component graph. So the problem remain is to know where the errors should be placed. If for this example, the two internal nodes, the edge is between two internal nodes, then the error is essentially put there. Otherwise, they will become a component. And the error that I just compressed is called optional error. You may put or not put an error on the phylogenetic tree. And the first step I introduced to you is compression process. So for component graph method, there are two key points you may concern. One is what is the component graph of a Go network? And another question is what is component? For this example, I define that a network is one component that if every reticulation is directly followed by a leaf, and I define the number of such one component Go networks, but I have restriction on the label of the leaves under reticulations into 1 to K. These graphs are the component of Go network. So if we do the process in opposite way, that means decompression process, we will directly have this equation. GNN, there's a simple explanation that you choose a phylogenetic tree for each internal node. You optionally choose J leaves to attach arrow on the phylogenetic tree and replace each internal node by component graph M. Okay, this is how we get the GNN. We use component graph method. And the next things we need to learn more about the component, how we estimate it. Actually, is from some kind of complicated recursion. And once we have the asymptotic result for this component graph, we may use the further formula to drive the asymptotic. We have to find an asymptotically matching upper bound and lower bound. Okay, this is our methodology. Next, I want to talk about our target, goal tree trial networks. As its name, the goal tree trial network is just an intersection of goal networks and a tree trial network. In the middle is a goal tree trial network. You may see the middle and the left and the right one just a little different. We just need to insert the new node with leaf to this edge. That will satisfy the tree trial property. Tree trial property once you have a non-leaf child, so you will get a goal tree trial network. So so we apply component graph method on goal tree trial network directly. So the first observation is that GTC is a goal network. So of course, is component graph method is a phylogenetic tree, possibly not binary. So the next question is, what is the component of it? Every one component tree trial network is also a goal network, but opposite way is not correct. This lemma will tell us that yes, our component of GTC is one component tree trial network with the same restriction on the label of the leaf on the reticulations. And directly from the decompression process of component graph method, we have this formula, which is extremely similar to GNN. We only change the component here. Okay, we still want to find the asymptotic of GTCN. So I want to calculate a rather easier object that is maximal reticulated GTC. I jumped the slide. So if I want to calculate GTCN, then I have to learn more about the component graph L. So if I remove the restriction of the label on the reticulation, it's an OTC. It's an OTC. The relation between OTC and L is really simple. We just relabeling. Because GTC have a well-known result. We have the result from 2021. And is well determined. And we have also the asymptotic for GTCN. And next, I want to talk about maxima reticulated GTC. A lemma says that maxima reticulation, the maximum number of reticulation of GTC is n minus 1, just like TCs. Also, the lemma reveals the structure that a component graph of maxima reticulated GTC is a phylogenetic tree, and each internal node have one pendant edge, and the other edges are have an error on it. That means we can calculate it. We set up the EGF for GTC n minus 1 and ln minus 1. The component graph method will tell us that this object is constructed by a single node, or you give me a phylogenetic tree, but I replace the root by component. But the component have one pendant edge, so it will be counted by 1. Then the other remaining edge are replaced by GTC n minus 1, divided by n minus factorial. That will reduce the, will deal with the order problem. And it actually can be simplified. As you can see, it is a Lagrange type. That means we can use Lagrange inversion formula, and we will simply get that GTC n minus 1 equals to this formula. So our next step is to find the coefficient here. Thankfully, we have a strong tool that is almost the same form, exactly the same form. And we just need a little asymptotic, we have the results. Here. So we have the results of maxima reticulated GTCN, GTC. The result doesn't have a stretch exponential part, but that doesn't matter. The next target, we just don't want to calculate n minus 1. We want to sum over k. That means GTCN. So recall the result of component graph method. We used the same two-step as Golden work did. So then our next step is to find the upper bound and the lower bound. The upper bound is quite easy because we just increase the age that we want to attach optional errors. So after some organization, this part is OTC, we have just learned. And this equation is defined as upper bound. The EGF of UN is actually also Lagrange type. So we just use the same process. We have the asymptotic. UN will asymptotic to this formula. This formula is quite interesting because it somehow inherit the both of stretch exponential and the multiplicative constant is determined. And the next step is we want to find a lower bound, but to not small. We restrict some component graphs here. The idea comes from the component graph, the dominating component graph of TC is actually a star component. Okay, but in GTC, we need a little bit more. We have we want cherry here, and we don't use Lagrange inversion formula, but we use Laplace method. You will eventually get the same result as UN, the upper bound. So the final result is that GTCN is asymptotic to this formula. And my third topic, I want to talk the GTC with field reticulation. A field actually is our original motivation to discuss about these classes of networks, because we found that if you fix the number of reticulation and you put n into and we have the asymptotic, that Pn is phylogenetic networks, and they have the same asymptotic as Tc. And in 2024, Fuchs and me, we found that the Go network actually have the same asymptotic. Actually, it makes some sense if you just a fixed number of reticulation. When n goes very, very large, then no reticulation will automatically satisfy your conditions, no matter how. They are very sparse. So in our results, GTCN have the same asymptotic. Okay. And the final topic I want to talk about is some randomness. I define the number of reticulation of a random network. And a known result is that from 2024, the TC networks have a limiting distribution. If I define more, I define inner reticulation. Inner reticulation means that the reticulation is not followed by a leaf. And we have a joint distribution for Go network. So what about GTC? Actually, we have the result for joint distribution here. The R is a standard normal distribution, and I is Poisson. Okay. This is the largest subset relation of different kind of classes of network. A little adjustment that you should delete this chain because they collect different objects. And there is a hidden top node. There is a phylogenetic networks without any restriction. Our a tree trial is important because it is a trial for many kinds of classes of network, and the Go network stay in a different chain. The reason why we don't concern about level 1, which is equals to Go tree network. Go tree network is not a tree; it's a network. It's level 1. Because the asymptotic of level 1 is more like tree, not networks. From this part is much less than this amount. So we don't concern GT. I mean, go tree network. I spoiled the surprise. You don't see anything. Okay. So yes, that's what I want to talk about. So wait. It's dedicated to Sheng because all of the author of this paper had been advised by Sheng. So thank you. And congrats. No, I say no.
Well, any questions or congratulations?
Yes, possibly on slide 7.
Shout it in the mic.
No. Blah, 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 blah. Yeah. So I believe it was on slide 7. Yes, I didn't get exactly what. So it was one where the green disappeared. So do you have several slide 7? Yeah. Yeah. Okay. So go back or go after. Yes, okay. Yeah. So I did not fully understand what was the model here and what was the role of the colors and in which way what you compress. So if it is short to explain or to explain again, perhaps you can comment on this. What is the role of the green stuff here? Why it is here and not here? Why the pink is here and here? What is the role of the colors?
Rule of the color.
How do you construct that? Sheng,
I like I
you cut the incoming edge of the this is the first step. And then it separated into many components, right? And each component is colored different, colored by different colors.
Compress it one.
Yes. And then you compress it into each component, you compress it into a vertex. So it will become a tree. If you have edge with the arrow, it means double edge.
And the green,
The green is actually, it should be like this.
Yes, okay, this was my question.
It's one in and one out. It's not we ignore this kind of structure. So if you have a vertex with one
you not
yeah. The structure is special here because only this kind of node will appear, right? Directly followed by a leaf.
This kind of,
so we especially ignore it.
Do these have some relation to
An official question?
Do these have some relation to lattices? It's
Yeah.
natural and useful, or are they naturally applied to the lattice, dealing with finite lattices? Don't know. Okay, it just looks like that to me.
Need to translate.
Representing lattice.